Good day everyone. Once again I welcome you to my page. In today's tutorial we shall be trashing out this gigantic logarithmic equation. And before we can start the solution of this, we must ensure we check for the domain. We must check the domain of this equation, either the base or that of argument as well. So let's check. So from here we could see that x cannot be equal to 1 here, because if x is equal to 1 here, that'll be 1 square, that is 1 minus 1, everything here becomes 0. So for the fact that this cannot be x, I don't need to check for this or check for this as well. So therefore our x must be greater than 1. Okay, good. It's not going to be equal to 1. Now let's check for 2, because we know that x greater than 1. Of course, what are the number greater than 1? 2. Let's check for 2. If you put 2 here, that will be 2 raised to the power of 2, that's 4. 4 minus 1, that's 3. So we are going to have log 3. Then putting our 2 here, base 3. Okay, noted. Now let's move on to this one as well. Putting 2 here, we have 2 plus 1, that's 3. 3 square, that's 9. So we have log 9. Then let's check for the base here. Putting 2 here, that is 2 minus 1. And 2 minus 1 give us 1. So here will be 1. Can it be equals to 4? No. Even from this statement here, log 9 base 1. Log 9 base 1 cannot be defined. Any number of base 1, of course, cannot be defined. Hence, our x here, the domain here also, x cannot be equal to what? 2. So it is possible 2 and above, 3, 4, 5, and so on and so forth are possible values of x, so that when we get the value of x, we can know which one to stick with and which one not to stick with. Now let's dive into the solution in details. All right, now let's take a look at this. From this left hand side, we can see that this is difference of 2 square. We can split it as log base of x plus 1, difference of 2 square, x square minus 1. That will give us x plus 1 multiplied by x minus 1. Okay, we are done with the left hand side. Now onto the right hand side, we see that, remember this law that says when your argument has a power, we return it here and it becomes the coefficient of the log. So we have 2 log x plus 1 base x minus 1. Everything here equals to 4. Okay, now let's see and look at this. These are multiplying each other. Okay, and remember that when we have log a, okay, let's say base x being added to log b base x, so they have the same base but different arguments. So we pick that one base, then we multiply the argument together. That will be a times b. So a times b give us ab. So the same thing that happens here, it means x plus 1 is multiplying x minus 1. So we can separate them by writing log the same base x plus 1, then x plus 1 plus log x minus 1 base x plus 1. Okay, then we are left with this. So let's write that back. We have 2 log x plus 1 base x minus 1. Everything still equated to 4. From our left hand side here, remember when the argument and the base are the same, then we have 1. Log a base a is equal to 1. Log s base s is equal to 1. So here we are going to, here everything here becomes 1. Let's transfer this 1 back to this side, then subtracting from 4, that will give us 3. So everything here will be equated to 3. So what do we have here? We have log x minus 1 base x plus 1 plus 2 log x plus 1 base x minus 1 is equal to 3. Now, if we take a look at these two, they have different bases. Of course, x plus 1 is not the same thing as x minus 1. We can decide to change the base. Remember that when you want to change the base, you can actually make, let's say where we have a condition like this, we have log a base x. If you want to change this base to be the argument here, and this our argument becomes the base, so we can easily write it as 1 over log x base a. So we can use this law. Okay, we can change any of this, either this or this. So I want to change this. Let me change this. So I will have, in my left hand side, I will have log x minus 1 base x plus 1 plus 2. Then I will write the reciprocal of, after changing this, you have 1 over log x minus 1 base x plus 1. Everything still equal to 3. All right. Now, from the look of things now, they now have the same base, x plus 1, x plus 1. Our intention is, if we have this, if they have the same base, we can perform operation between them. Okay? Everything now is having what? Base of x plus 1. So, let's see. We can represent this by a variable. Let's call this here as y. Let's call it y. So if we have that to be y, definitely only here will be ordinary y plus 2, and everything here becomes y. Then that will be 1 over y. 1 over y is equal to 3. So definitely what we have here eventually becomes y plus 2 over y is equal to 3. Okay, now let's ensure we clear the fraction here. If we clear the fraction here, we can multiply through by the denominator here. The denominator here is these ones. The denominators here are 1, y, and 1. So our LCM is y. So if we multiply through by y, so that we can have a simplified form, multiply through by y. So if we multiply through by y times y will give us y square plus ordinary 2 is equal to 3 times y will give us 3y. Hence, what we have here becomes a quadratic equation. So we have y square. Let's bring 3y in. So we have minus 3y, then plus 2 is equal to 0. So if we can find the value of y here, then we equate it back to the value of what we used to represent y. Okay, now here, from the look of things here, if we factorize this here, our y will be the two numbers that can be multiplied, that will give us 2, but that can be added, that will give us minus 3. And that is minus 2 and minus 1. So solving this further, we will see that y minus 2 is equal to 0, or our y minus 1 equals to 0. So therefore, here our y is equal to 2, or y is equal to 1. So these are the two possible values of y. We are not done. We are moving to find the value of s. We are not given y, we are given equation in terms of x. Now recall that y is equal to, we use y to represent log x minus 1 base x plus 1. So at y is equal to, we gotten y to be 2 or 1. As y is equal to 2, so therefore it means log x minus 1 base x plus 1 is equal to 2. Recall the law that says if you have log b base x is equal to y. So therefore, we can transform logarithm to indices. So therefore, our b is equal to x exponential y. So that is the same law we are going to apply here to solve for the value of x. So therefore, our x minus 1 will be equal to x plus 1 then exponential 2. So let's simplify the right hand side and let's solve. So we have, if we expand this bracket, we are going to have x squared plus 2x plus 1. Okay, now we are moving to another quadratic equation entirely. So collecting all this term here, bring it to this side. So we have x squared plus 2x. So we have minus x here, then plus 1, then plus 1 from this side as well. So what we have there. So our quadratic equation will now be x squared plus 2x minus x, that will be x plus 2. Don't forget it's going to be equal to 0, equal to 0. So here is the quadratic equation we can solve to get the value of x. But from the look of this quadratic equation, it's not factorizable. So we can easily use our general formula that says that x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. In this case, our a is 1, the coefficient of x squared. Our a is 1. Then our b is also 1. B is 1. And finally, c is equal to the constant term there, 2. So substituting this into the value of this equation formula, then we have minus 1 plus or minus square root of 1 square minus 4. A is 1 and c is 2. Everything over 2a, and 2a is 2 times 1. So here we are going to have minus 1 plus or minus the square root of, what do we have here? This is 1. 4 times 2, that's 8. That will be 1 minus 8. That will give us negative 7. Everything over 2 times 1, 2. So therefore, our x here will be negative 1 plus negative root 7 over 2, or x will be minus 1 minus root negative 7 over 2. So this is going to give us a complex root 7. That will be, of course, that will be what? Root 7i. Root 7i, where I is negative 1 over 2, or x will be negative 1 negative root 7i, everything over 2. Okay, now if this is the first set of values of s, okay, also when y is equal to 1, so when y is equal to 1, so therefore when y is equal to 1, we shall have that as well. Therefore it implies that x minus 1, we transform it to initial equation. That will be x plus 1 exponential 1. Okay, so here we're going to have x minus 1 is equal to x plus 1. Anything exponential 1 still remains itself. So we can see that when we have something like this, our x value is, we can't determine here, because if we decide to collect the like times, okay, we decide to collect the like times here, it means x comes to this side becomes x, and this 1 becomes plus 1. Okay, So getting to this point showed that there is no solution for this when this whole expression is equal to 1. That is, at y is equal to 1. But let's go to back to the previous set of values of x that we have. X is equal to minus 1 plus 7 root 7I over 2, and also x is equal to minus 1 minus root 7I over 2. These values, they are not real. They are not real. They are imaginary values. They are imaginary numbers. And hence, recall that we have declared our domain to be greater than 1 but not equal to 2. But all these values here, the values here are imaginary and they are all negative values. They are all negative values. Hence, this equation has no real solution. The equation log x squared minus 1 base x plus 1 plus log x plus 1 over raised to the power 2 base x minus 1 is equal to 4. It has no real solution. This is Oasis Online Math. If you enjoy this content, please don't forget to drop your comment and follow us on all our social media and the YouTube channel as well. Thank you very much. God bless you. See you in the next class.